So continuing on in our two sample hypothesis test, this is our first scenario where we have dependent samples. So just as a reminder, these are samples that have a before and an after, a pre and post, an old and new. It is the same subjects being measured twice with some time period in between. So there's a little bit of differences with this section because of the setup of the problems where you are going to have the original data set. So you are going to have the before and the afters so that you can find the differences between these values. So one of the first things we're going to need to do is we're going to need to find the variable D, which is the difference between your before and your after. So this would be like your before minus your after. Once you do that for all of our data pairs, then you're going to be able to find the mean. So D bar, similar to our X bar, it's the sum of our D's divided by our sample size. So when you are looking at these problems, you're going to notice that there is no mean and standard deviation given to you. You have to find them before we can do our test statistic formula. So the conditions that we need to be able to meet is that it is random. You're going to notice it is dependent. And again, you're going to see the paired data in a chart of some sort. It is either going to say normally distributed or the number of data pairs needs to be at least 30. Most of these problems are going to say normally distributed because a data set of more than 30 is a lot of work for you to do. So I tried not to give you too many large problems. So they're going to say kind of small. Typically, our sample size is no more than 10. So you're going to see that phrasing normally distributed with these. And because we are using a t-distribution, our degrees of freedom is back to n-1, where n is the number of pairs. So some of our symbols, just to reiterate, n is our sample size. We've seen that one many times. D is when we take the difference between each one of our paired datas. So the before and the after, the old and the new. Mu D is the hypothesized mean of the differences of the paired data. But for us, this is kind of like our population mean in the back of the formula. We are going to have this one set equal to 0 for each one of our problems. And then again, you're going to have to find the mean. You're going to have to find the standard deviation. I am going to show you how you can find it with your calculator. But in case you like to do it with the formula, this is our formula to find D bar, the mean. And then this is the formula, the one on the right, how you're going to easily find the standard deviation. So using the sum of D squared and the sum of D with our sample size. So again, we've got D bar, we've got our test statistic. It looks like back in the day when we were doing a t-score and a z-score. So our sample minus our population means on top over our standard deviation over the square root of n. And then again, our degrees of freedom. So we're going to check conditions, write our hypothesis, note our level of significance. So we can use our inverse t to find our critical value. We're going to sketch it. You're going to have to calculate the mean and standard deviation, then the test statistic to compare to our sketch to see if we're in the rejection region or not, and write our conclusion. So here's our first example. A shoe manufacturer claims that the athletes can increase their vertical jump heights using the manufacturer's training shoes. The vertical jump heights of 8 randomly selected athletes are measured. After the athletes have used the training shoes for 8 months, their vertical jump heights are measured again. The vertical jump heights in inches for each athlete are shown in the table. The level of significance of 0.10, is there enough evidence to support the manufacturer's claim, assuming the vertical jump heights are normally distributed? And then you have a chart here for all 8 of your athletes, both their old score and their new score, or their height when they were jumping. So the first thing we need to do is check our conditions. It does say that we have random selected these 8 individuals. It is normally distributed. You can see from the chart the old and new scores for each athlete. So that means it's dependent. And we do not have a population standard deviation. So no population standard deviation. That's because you are going to have to find the sample standard deviation in a minute. So that's all the conditions that are letting us know this is a t-test. Now we're going to use the information from the chart. We see our level significance in here. Again, from looking at the chart, and just to reiterate, your sample size, your N, is 8. You have 8 athletes that have then just been measured twice. So our sample size is 8. And the term that we're looking for in order to know how to do our hypothesis, our inequality term, you're going to notice with dependent, you're going to see things as increase or decrease. Do we want our numbers to get higher or do we want them to get lower from our before to after? So in this case, it does say increase. That's what we're claiming, that we can increase their vertical jumps. Now, when you're writing HOHA, we use mu1 and mu2. In order to put increase in here, you kind of have to think about it a little bit. So I'm going to do a little sketching off to the side here. If I know that I can only jump 10 inches, and then I use their shoes and I increase my jump to 12, I've gone up. I've done what they've claimed that I can do. But what symbol would go in between them? Would it be less than or would it be greater than? If I want to increase, it is less than. So this is to increase. If I wanted to decrease, say our scenario maybe was I had a 10, maybe it was a golf score and I wanted to get better. And maybe the next time I went golfing, I decreased it to a 6. If I decrease, then I'm actually using my greater than symbol. So it almost feels a little backwards, but sometimes when you put numbers into play, it might make it a little easier to see. So because we do want to increase, I am using my less than symbol in my HA. My complement is greater than or equal. Now, one other thing that you might notice when you are working on these in my stat lab, sometimes they use mu1, mu2. Sometimes they make your hypothesis with mu d and 0. So in case you see that come up, what's happening is they are taking that mu1 and mu2 and they are truly subtracting it. They are moving that mu2 to the left-hand side, so mu1 minus mu2, less than 0, and then they're changing that subtraction into mu d, d standing for the differences between them. So what you'll notice is the symbols themselves aren't going to change. Once you've determined it's the less than because we're trying to increase, it's going to be the same thing, whether you write mu1 and mu2 or if you write mu d and 0. But I wanted to make sure you've seen that before you get to your homework and that throws you off. So either way you want to write your HOHA for this section, this is the only section that has this kind of alternative option. You can do it either way for me. I don't mind either way. So I'm going to erase some of this so we have a little bit more space. The next thing we want to do, once we've determined our HO on our HA, our hypothesis, we need to jot down our level significance. So in our case, it was 0.10, and make our sketch. So for on our sketch, we always look at HA to know our shading. So less than means left tail. We're using inverse T. So we're going to plug in all of alpha. And then our degrees of freedom is N minus 1. So our sample size was 8. So N minus 1 is 7. Round off our answer to 4 decimals. We get negative 1.4149. So that is the area under the curve. If we get anything smaller than that, we are going to reject. Anything bigger, we fail to reject. So the next step we need to find is our mean and our standard deviation. So if we make a little chart, make 4 columns, our old score, our new score, our differences, D, and then D squared. So if I start to copy over some of the scores, I'm just going to do the first couple rows here. Our old score was 24, 22, then 25. The same paired new score was 26, then 25, then 25. In order to find the D, it is the old minus new. So for the first row, 24 minus 26 gives me negative 2. 22 minus 25 gives me negative 3. 25 minus 25 gives me 0, and so forth. That is how you find the differences for each one of our pairs. Now keep in mind, to find the mean, you're going to add up all of those differences and divide by n. So going through the motions and doing all of those values in that D column, we add them up at the bottom, we get negative 14. So negative 14 divided by our sample size of 8, get negative 1.75. This is our sample mean. Now the next thing we need to find is our standard deviation. So I'm going to copy over that formula. It's the sum of D squared minus the sum of D. We're going to take that value to square, divided by n, and that whole thing is over n minus 1 underneath a radical. So for that, that's why we have this fourth column of D squared. So you take each one of the values in the D column and you multiply by itself. So negative 2 times negative 2 makes positive 4. Negative 3 times negative 3 makes positive 9, and so forth. All of these values should be positive. So I'm making your little note there, positive numbers in that column. So when you add them all up at the bottom, the sum of D squared would be 56. So that's after doing it for all 8 of them. So I have what I need to plug in. I can plug in 56 for the sum of D squared, negative 14 for the sum of D, which I will then square, divided by 8, and the whole thing is over 8 minus 1 underneath my radical. Type it all in at once, hit enter. You should get 2.1213. Now, a little shortcut to check your work. You can type these 4 columns, the old, the new, the D, and the D squared, into your calculator. You could put all of your old values in list 1. You could put all of your new values in list 2. Then at the top of list 3, you can type in L1 minus L2 and click enter, and it will automatically autofill your differences. Same at the top of list 4, you can type in L3 squared, hit enter, and it will autofill all of your D squared values. So if you put this into your graphing calculator, once you've got list 1, 2, and 3 in there, you can go to one var's stats on list 3, and the X bar is your D bar, and the SX is your standard deviation. So you can check both those values real quick. Both of them should come out exactly the same. Either method works, whether you want to do it by the formula or use your calculator. Now, we're not done. We've got our mean and our standard deviation, but now we've got to actually do our test statistic. So our formula, T equals D bar minus mu D over our standard deviation over the square root of n. So we can plug in our sample mean, minus 0 for our population mean. Plug in our standard deviation, our sample size. Again, you want to do this all in one go. Click enter once, and we get our test statistic. This is the number that we're comparing to our sketch. So I'm going to just copy our sketch over here just for quick reference. If you're comparing your test statistic to your critical value, we are in that shaded area somewhere. So because of that, we are going to reject. So at 10% level of significance, there is coming from the fact that we rejected. There is enough evidence to support the claim. Support is because HA is our claim. Support our claim that, and then we'll put ... Let's go back to the wording of our problem. They are claiming that the athletes can increase their vertical jump heights using the manufacturer's training shoes all the way to the period. Again, that's showing what your inequality term is. So in this case, we are increasing and we're talking about the athletes' jump heights. It tells you the context of our problem here.